with. So we want to consider the region. Let's see, am I indeed recording now? Yes, and I have audio. Okay. Whoa. All right, so make a sketch of those curves, those functions near the origin, and take a look at the region we're going to try and find the area of. I'm going to try a couple different things on it. Hey, Jesus. All right, so there's x plus y equals 2. Y equals x squared. And then y equals 0 is the x-axis. So we want this region right here. And we could restate x plus y equals 2 as a function. So if we do that and we solve for y, we get y equals negative x plus 2 if we put it in slope-intercept form. And so the one way to think about this area is y equals x squared is in control of the upper boundary up until we get to 1. After 1, the blue curve takes control of the heights. So in terms of using an integral to find this area, one way to do it would be with two different integrals. One integral from 0 to 1, where x squared is the function of integration that's going to help us find the area. And then we continue on with the integral from 1 to 2 with negative x plus 2 representing the height of our rectangles. So sometimes we have to break up areas based on intersection points if the boundaries shift. Which function gets to be on top or the bottom, it kind of depends on the orientation of the figure. So do me a favor, find some antiderivatives for those two and see if you can come up with a value of these definite integrals to represent the area. And then we'll put a little twist on it, see what happens. So I think if I didn't screw up my arithmetic, the answer is 5/6. Anyone else get that? Okay. So you want to carefully evaluate at each point. We want to use parentheses carefully when we have subtraction. Here, recall the method for using different kinds of separators. We use square brackets before we evaluate. After we evaluate, we use curly brackets or regular parentheses to keep things in line with signs and multiples. So a couple of us got that answer, but I still have no idea if we're right. We could be just like have the same delusion. Any questions on what I have here so far? So once we have an antiderivative, it's a matter of careful arithmetic. Whipping out a calculator at this point isn't a bad idea. So I'm going to double check it with GeoGebra. Where is my, oh, I moved it. Actually, before I jump to technology, let's just do it a different way and see what happens. So I'm going to redraw this. So that's the region we're trying to find. We have x, we have x plus y equals 2, we have y equals x squared, and the y-axis up there. So calculus introduces us to the idea of forming our rectangles vertically, leading to the integral with respect to x. However, there's no reason that we can't make the rectangles horizontal instead. If we do that, then our height would be some x distance, and our width would be a delta y instead. So it turns out we can integrate with respect to y instead. The nice thing about integrating with respect to y instead is this curve right here is on top the whole time as x increases, and this curve right here is at the bottom the whole time. So if we write these as functions of y instead of functions of x, we can do it in one integral. Okay, so what would happen if I solved that one up there for x to get a function of y? I get the square root of y. Now it's plus or minus. I only care about the positive one. I only want this side right here. So as far as we're concerned, x equals the square root of y is sufficient. We don't need the negative square root of y, which lives out there. And then here, it's not too bad. I just solve for x instead of y, and I get a pretty similar thing to before. I get x is equal to either 2 minus y or negative y plus 2. I'm going to write it as 2 minus y this time. And I know this function right here is my upper bound, and this one is my lower bound, again, with x increasing like that. And then I just need to integrate as y goes from 0 to 1. Okay, so then I think the integral should look like this. And I'm just going to make a note. I'm integrating with respect to y, because typically these boundaries are x. Right? So a lot of times when we switch variables, we make a note so everyone's clear. And then we take the upper function minus the lower function. So the upper function is 2 minus y minus the lower function, which is the square root of y. And I'll put that whole thing in parentheses dy. So I should be able to get the same result by evaluating this guy in one shot. So give it a try, see what happens. Find an antiderivative, evaluate at the endpoints, see if we get the same number. And here I find it helpful to think of the square root of y as y to the 1/2. So I believe that's one version of the antiderivative, an antiderivative. Anybody else in agreement? Jesus likes it, okay. Thank you. And so now we plug in the endpoints, and 0 is a nice endpoint to plug in here, isn't it? Love that. So let's see, what do we got? We've got 2 minus 4/2 minus, did I do that right? Oh no, sorry, 1/2. Wrong boundary in my head. Minus 1/2. And then minus 2/3. And let's see, what does that give me? That gives me 2 minus 1/2 would be 3/2. Is that right? So 3/2 minus 2/3. Common denominator would be 6. So this is then 9 minus 4/6. Hey, which is 5/6. Nice, it works. Fractions being the biggest impediment here. Did I skip anything and lose anybody here? We all right? So the cool thing is that if we have a complicated region to evaluate for area, we can make the decision to integrate with vertical rectangles with respect to x or horizontal x with respect to y. Hinges on a couple of different things. Is it easier to break the integral up into pieces, or is it easier to switch the function to the inverse function to try and come up with it? It just kind of depends on the situation. But we got another tool for which to help us try and get an answer. And the thing is, you never know what's the easiest way till you do it both ways. What do you think here? Was the integrating with respect to y easier than with respect to x? Or was the other one easier? Curious. Raise your hand if you think the first version was the easiest. You got 1, 2. Raise your hand if you think the second way was easier. And we got a couple no comments, not sure. Yeah, sometimes it's a toss-up. They're both like, you think it was like they're both about the same. Yeah, sometimes it doesn't matter, sometimes it does. But the bottom line is there's nothing special about x. We can integrate with respect to any variable, provided we can represent that variable in terms of some useful functions. Okay, so I got it 2 different ways. I'm pretty sure it's right. I don't think I even need GeoGebra. But in the spirit of just playing around, it's always a good thing to practice. Let's see, it's a good idea in GeoGebra to type your function in first. So let's use the x² version and the 2 minus x version. And for GeoGebra, if I do f minus g in the integral, it will create a whole new function like we saw the other day. So if I wanted to actually shade this, I'll have to do the integral in 2 parts. I'll have to first integrate, let's see, which goes first? Square. So f goes first from 0 to 1. And then I complete with the next part. Then we take the integral of g from 1 to 2, and it gets the rest of it. So here, GeoGebra is telling me that it's a third plus a half, which we came up with the first way we did it, and a third plus a half ends up being 5/6. Oh, integral between. I haven't used that. So for that one right there, we would probably have to write it as functions of y, which GeoGebra couldn't do. Because in terms of integral between, it wants a top curve and a bottom curve, which we don't have here. So that function wouldn't work. It would work with the example we used the other day. So let me bring a new window up here. So if we had a definite top curve, like the other day, we had 1 minus x squared on top, and then we had x squared minus 1 on the, x squared, there we go, minus 1 on the bottom, and we're trying to find the area in between. And so that integral between should work on this, and I forgot GeoGebra had that. So if we select that, the upper function is f here, the lower function is g here, and we want to go from -1 to 1. So that's a nice feature there. And then it shades the right area. Cool, thanks for pointing that out, Stanton. And in case we come back, let's blow up the font. Come here. All right. Any other questions besides the one I asked so far? Anybody think of any? Not yet. Okay, let's see. I could have sworn I had another tab up with stuff in it. Where did it go? Didn't I have Canvas up here a few minutes ago? I must have closed it. All right, let's see if I had anything cute in my notes. Oops, wrong site. No, I want either. Um, 5, 6. Did that one. Did we do the cosine squared yet? I don't think we did. We just did that one there. Okay, let's try cosine squared and 1. New page. So we want to find the area between y equals 1 and y equals the cosine squared of x on, I think it was from 0 to pi. Is that what I wrote down? Yep, 0 to pi. And just for fun, does anybody remember an identity related to the cosine squared? No, it's 1 minus sine squared, but that doesn't really help much. There's one in terms of the double angle formula. So if you think, let's just do a little trig review just for fun, because we're going to need it soon. Oop, wrong button. So normally I just look up identities when I can't remember them, but the cosine double angle formula, so cosine of 2 theta, there's a couple different versions of it. One is that you have the cosine squared of theta minus the sine squared of theta. And then if you combine that with the Pythagorean identity that says cosine squared plus sine squared is 1, you can substitute out either the cosine squared or the sine squared. So if I wanted to get rid of the sine squared, I could replace it with 1 minus the cosine squared. If I do that, then I can rewrite this as twice the cosine squared of theta minus 1. And this is the source of what's called the half angle formula in trigonometry. So if I solve this for the cosine squared, then I'm going to get that the cosine squared of theta, I'd have to add the 1 to the other side, right? So I'll have a cosine of 2 theta plus 1, and then I would have to divide the 2 over to the other side, so over 2. And if we were to, for example, let x equal 2 theta, then theta would have to be x over 2, right? So rewriting that, that would give me the cosine of x over 2 is equal to the cosine of x plus 1 over 2. And to get rid of the square, I take the square root of both sides. And so that's what's commonly called the half angle formula. And I don't know about you, but sometimes I have troubles remembering which part is positive, which part is negative, what order the subtraction goes in, little details like that. So if I don't have a trig table nearby to look up, for example, the half angle formula, for some reason, this one right here always stuck in my head, and I can turn that into a whole bunch of other trig identities that are very common. Anyway, why is this useful for us? Well, in a minute, we're going to have to integrate cosine squared, which is a bit of a problem because of the square. And so somehow we have to get rid of the square. We could try substitutions, like a U substitution. But a trig identity is also a substitution, isn't it? We're claiming that this thing is equal to that thing. Okay, so substitutions aren't always just U substitutions. They're any algebraically equivalent thing that you could use. Okay, so substitution is a little broader than what we've been talking about earlier. Okay, so we're going to need trig identities occasionally when trig functions pop up. All right, so let's whip out a graph of this. And just noting again that the cosine squared of theta, I'm going to write it a little bit different. I'm going to write it as 1/2 times the cosine of 2 theta. What was it, a plus 1/2? So if I just consider dividing this 2 here into both pieces of the addition, that would be another way to look at it. What's the period of this function right here? Almost, not pi over 2. Normally the period's 2 pi, right? Yeah, and then whatever the multiplying factor is up there cuts the period. So it'd be 2 pi over 2, it'd be just pi. So because of that 2 right here, the period is going to be pi. Does anybody know the amplitude of this by looking at it? The amplitude is 1/2. Yeah, that's the multiple out front. And then this 1/2 just lifts the whole thing up. So based on looking at it there, I can do a rough sketch of it without using my calculator. So I believe graphing this thing, it's going to go from 0 to pi for a single period. Pi over 2 will be in the middle. It has an amplitude of 1/2 centered at y equals 1/2. So if I put y equals 1/2 here, y equals 1 would be about there. And so this would be the center line of the graph, and this would be the max the graph can achieve this particular function. Where does the cosine usually start? At its midpoint, at its peak, at its bottom? At its what? It starts at its peak. So that means to make this graph, I would start up here. If the period is pi, I will end right there. And if those are the two peaks, the minimum, has to occur down there. And then it has to have its midpoints in here at pi over 4 and 3 pi over 4 over there. And I have an extra point accidentally. Ignore that. So this graph has to cycle through like that and keep waving forever and ever like that. So that's one complete cycle of this function. And on the previous page, I wanted to find the area between this function and y equals 1. And so that means I'm looking for this area right there. And so there's a variety of ways to approach this. Did anyone graph this and double check that I didn't just make all that stuff up? It's not always a good idea to just believe me. I do make mistakes on occasion. So I'm going to ask GeoGebra just to make sure I wasn't lying with all that, but it looked pretty good, didn't it? All right, let's get rid of these guys. And we're going to graph cosine of, oops, x. Whoa, what are you doing out there? Oh my, that's not going well. Hello, GeoGebra, stop it. Okay, let's just start over. Cosine, I wonder if GeoGebra can handle that. Squared of x. Oh, GeoGebra is not happy about that. Interesting. Yeah. Now it's just totally mad at me and it refuses to cooperate. Cosine of x squared. Okay, there we go. And then my claim is that this thing, if I go up to x equals pi, is one complete period. Okay, so that's what we graphed. And then we are comparing that to y equals 1. And so looking for this area right here. All right, so my picture's not perfect, but I have all the right points to start with. So what's our integrand going to look like? Yeah, the 1's on top, so we got to do 1 and then minus the cosine squared. So first glance, the integral goes from 0 to pi of 1 minus the cosine squared of, let's say I wrote a theta in there, so theta d theta. Some other things to consider. Is there any symmetry here? Okay, where does the symmetry lie in this particular shape? Is there a line of symmetry somewhere? At x equals pi over 2. So we could, I know I don't mind integrating from pi to 0. We could double the integral from 0 to pi over 2 if we wanted to. But I don't know if pi over 2 is any easier to plug in than pi. So that doesn't really help us too much. But it's always good to consider symmetry. Other things to consider is, do we know antiderivatives for these things? Like, do we have an antiderivative for 1? Yeah, it's just going to be theta. Antiderivative for cosine squared. Can you think of a function whose derivative is cosine squared? Nothing comes to me off the top of my head. Sine cube. Well, no, because sine cube is going to involve the chain rule. So you'd also have a cosine as a multiple of that, right? So that's one thing. So if I did stop here and consider, well, maybe a u substitution might work, like if we let u equal the cosine of theta, then du, what's derivative of cosine? Negative sine, there we go. Negative sine of theta, d theta. Is there a negative sign hanging out anywhere in that black stuff? No, so that was a bad idea. That didn't work. Okay. And if we tried taking the derivative of the cosine squared, it gets even worse. So a regular u substitution doesn't work. So if that's the case, what's my fallback? Well, think back to Calc 1. You got to whip out a trig identity, which we already did earlier. There's a trig identity we can apply instead. So a u substitution, anything standard is not going to work here. We're going to have to do a substitution based on a trig identity. So we're just going to, in place of the cosine squared, we're going to drop that sucker in right there. So rewrite that integral, see what we have. oops, wrong way. So I now have the integral from 0 to pi of 1 minus 1/2 the cosine of 2 theta. And then that would have been a plus 1/2, but I have to distribute the negative, so I think it's a minus 1/2 d theta. Did I get that right? Samantha, what do you think? Right here? You think the minus is incorrect? So let's see, back a page. So I'm replacing this guy here with all of that. So originally it was a plus, but when you do a substitution, you got to put it in parentheses. So we're going to have to distribute that minus through there. Yeah, so we want to be careful. So I'm pretty sure, does that seem better now? So that's going to be a 1 minus 1/2, right? 1 minus 1/2 is 1/2. So ultimately it cleans up to 1/2 minus 1/2 cosine of 2 theta d theta. Now it's not so bad. Although, let's see, thinking about this for a minute, let's see, derivative of sine is cosine, right? So the sine is going to have something to do with this here. But what's the derivative of the sine of 2 theta? Chain rules involved here. Yeah, so I kind of need a substitution for that 2 theta right there. So just note, if u, let's switch color, if u were equal to 2 theta, then du would be a 2 du. Do I have a 2 hanging out here? No, but we can make it. We could write this instead as 2 fourths, which is the same as 1/2. However, it gives me the desired 2 that I want. All right, so I could tweak it a little, or I could continue to, I didn't carry through with the substitution. I'm just using the substitution to note I am missing a multiple. Okay, so I'm going to throw it in that way. So then I think the antiderivative here is going to be 1/2 theta for the first part. To take the antiderivative of cosine of 2 theta, that 2 has to be a part of it. So that stuff I circled in blue is the derivative of the sine of 2 theta. Okay. The things I didn't circle are the negative and the 1/4. Okay. Now, I'm going to double check that I'm correct in there, because just like having troubles with positives and negatives, multiples can be a problem. If we take the derivative of 1/4 sine of 2 theta, what happens? Well, the 1/4 just hangs out, right? It's just a constant multiple. Derivative of the sine is the cosine. 2 theta stays in there. And then the chain rule says I have to take the derivative of 2 theta, which is 2. Cleaning up the constants, I get 1/2 cosine of 2 theta. So did I deal with the multiples okay? Yeah, and that just takes practice. The more you do of it, the more you get used to playing around with them in there. If what I just did just blows your mind and it doesn't work for you, then what you do instead is carry through with this substitution and put u's in there, and then reverse substitute later. Then all the constants just work out nice. It's a couple extra steps, but it's safe. Okay, so at this point, I'm pretty confident in my antiderivative. So then I plug in my boundaries. So I don't know if I have enough room, but we'll try. Plugging in pi, I'm going to get a pi over 2 minus 1/4 the sine of 2 pi. Sine of 2 pi is 0. So I have 1/4 of 0 there, which is lovely. And then I'm going to have minus, and anytime I do the second boundary, I always put a parenthesis around it. be safe. Plugging in 0 here is wonderful. I get half of 0. And then what's the sign of 0? 0. Yeah, so I get a quarter of 0. And so I have a minus 0 there too. So that part turns out to be irrelevant. I just plugged it in to double check. And so it looks like the answer is pi over 2 is the only thing that's left standing. So that was pretty complicated, lots of room for mistake there. I have a couple of options. I could do it again, carrying through with the substitution, and or I could plug in GeoGebra. Just to do the substitution, I'm just going to double check that to make sure it works. So new page, oops, new page, there we go. So we've got the integral from 0 to pi of 1/2 minus 1/2 cosine of 2 theta, is that right? Anytime we have a function within a function, it's a good time to consider a u substitution. And so here we would say let u equal the inner function 2 theta. That implies that du is equal to 2 d theta. Now that 2 is missing on the outside here. So what I would have to do is rewrite it as d theta equals 1/2 du if a piece is missing. And this right here only applies to that chunk right there. And I'll have to come back and look at the rest after. So then if I am integrating, let's call it 1/2 the cosine of 2 theta with respect to theta, that's equivalent, according to my substitution, of, now that 1/2 is stuck here, I'm going to put it there. Cosine of 2 theta becomes what? Cosine of u. And what is d theta equal to? 1/2 du. Right, so that 1/2 just gets carried along as a quarter. Right, and the antiderivative of the cosine is the sine. And then since I don't have boundaries here at the moment, I technically have a plus c there. Okay. And then reverse substituting, u is really what? 2 theta, so reverse substituting, this is really, for an antiderivative, 1/4 the sine of 2 theta plus c. So what I'm doing here is I'm confirming with a u substitution that an antiderivative for that chunk right there is that thing right there. And the fundamental theorem for evaluating an integral says you need any antiderivative will work. So we can just let c be 0 in that case. And we're okay. Okay, so that takes us back to right near the end of the other way we did it. All right, how are we doing on time? We got time for one more, perhaps. Let's see. So nobody can think of anything that was particularly challenging in the homework? There was one. Okay. Let's jump in and pick something. All right, so somebody pick a number in the 20s. Let's go with 24. 24 has lots of divisors. It's a lovely number. Okay, find the area of the region enclosed by y squared minus 5x equals 9 and x minus y equals 1. Oh, so we have a sideways parabola there. Okay, that's a good one. Let's take a look at 25. 25 has us working with natural logs, which is always interesting. I think I'm going to go with 24. All right. What's that? I'm afraid of natural log. No, I love the natural log. It's beautiful. So let's make a screenshot of that sucker. And see if we can sketch it. So I think the hardest part about this one is sketching it and deciding which way to integrate. Okay, so those are our functions. And we want to go between them. So I'm leaning toward graphing this with respect to y, so functions of y instead of functions of x. Otherwise, I have plus or minus the square root to deal with. That might not be bad either. I think I'll solve for x. So if I solve for x here, then I get, on the other side, a 9 minus y squared over -5. Oh, wait a minute. Solving for x, subtract that over, divide by -5, which could be rewritten as 1/5 y squared minus 9/5. Eek, fractions. Alternatively, we could solve for y, in which case we would get plus or minus the square root of 5x plus 9. Which one would you rather play with? Solve for x. Okay, Stan, I'll let you pick that one. All right, so this is a sideways parabola. It shifted, let's see, up 9, no wait, this is with respect to x. So it shifted left 9/5, and it's narrow because the multiple of 1/5. So let's get a sketch of that. So then the vertex of this is going to be 0, -9/5. So I got to come this way. So 9/5 is what? -1 4/5. So if I scale by, say, 2, 1, 2, 1, 2, the vertex is about over here. We'll do this sucker in red. Vertex is about there. And if we let x equals 0, which puts us on the y-axis, this one is useful, because if x is 0, we get plus or minus the square root of 3. So 1, 2, 3, 1, 2, 3. So we have more points here and here. So here is that parabola roughly, something like that. And what's our other function? X minus y equals 1. So there, to pick you in blue perhaps, if x is 0, y must be -1. And if y is 0, x must be 1. So we get this line here. Does that look right? Yeah. Oh, yeah, y equals x minus 1. Looks right to me. No? So we want the area of that region right there. So if we integrate with respect to y, is there always a top function here for rectangles in this direction? Yeah, the blue function is always greater than the red function in that region. And so then it's a matter of deciding where we're integrating from and to. Do we already have the bounds of integration established, or do we have some more work to do? Yeah, the bounds of integration are going to be the points of intersection. So we're going to have to calculate those 2 points of intersection. So one way to come about this right here would be to integrate from this y value to this y value with the blue function minus the red function. Okay, so that's one way to do it. Other way is to think vertically. If we do it vertically, is there always a function on top, or do they switch? Well, vertically, yeah, there's kind of a change going on. Over here, vertically, the red is above the blue, but over here, it's the two different parts of the red that dictate it. So I'm gonna have to separate it as part of the plus and the minus, so I'm gonna have to break this into multiple integrals, okay? So I'm thinking that the horizontal rectangles are the way to go here. That looks slightly easier to me. All right, so let's set it up. So we're gonna have to set these equal to each other and solve. So let's see. And we want to end up with the y values. So I think I would be inclined to solve this guy right here for x, and then substitute into that one, and then I can calculate the y's. What do you think? Reasonable approach? All right, so y squared minus 5x equals 9. Y squared minus 5x equals 9. And according to our other equation, x would be y plus 1, right? And so we're going to drop in here, x equals y plus 1. So then we get y squared minus 5y minus 5 equals 9. What do you want to do, quadratic formula or complete the square? Oh, okay. I love completing the square, but that's all right. So we will bring the 9 over. So then we have y squared minus 5, what's that, minus 14 equals 0. All right, plug her in. See what you get. Oh, so let's see, 14 times 4 is what, 56? It's 25 and 56. Ooh, that's nice. 81 inside? So that actually factored. Oh well. So we've got, anytime the root simplifies, so it looks like we have 5 plus or minus the square root of 81 all over 2. See, 5 plus 9 is 14 over 2 gives us a 7. All right. And then negative 4 over 2 is a negative 2, I think. And oh yeah, totally see those factors in here now. Okay. Anybody see that before we did this? You guys already saw that? Good job. All right. So do those seem reasonable according to our sketch? Negative 2 totally seems okay. And the 7 seems a little sketchy to me, but could be I just have a bad picture. My scale's not very good. I really only plotted 3 points here to get the parabola. Yeah. All right, I'm just going to hope it's right. So what do we have then? We have the area should be the integral from negative 2 to 7. The blue function is the greater xy's. We have functions of y here. And it would be represented as x equals y plus 1, right? So we're going to have a y plus 1 minus my other function, which is 1/5 y squared minus 9/5 dy. So like I mentioned a minute when we first started this, the hardest part of this problem was setting up the integral. because we had to evaluate the region to decide what our boundaries were in terms of functions and endpoints. So we are at a time for fun with math. Please take this one home and come up with a number. We'll debrief on it tomorrow. So tomorrow is Wednesday. So my inclination is to keep the test on Thursday unless somebody has a good reason to do otherwise. Because I've covered just about everything I need to cover in chapter 5. It's just a matter of people finishing their homework. I know Darren has an objection to Thursday because he'd rather not take the bus in just for this class. And I'm all for minimizing travel from Oregon, especially. That's a long way. So either we have it on Thursday and we just move on next week, or we have the test on Monday and we start chapter 6 on Thursday. Should we make this a democracy?
I like Thursday better.
Get it done on Thursday? All right, let's get the test done on Thursday. So a couple of things you need to do to review. There's the review exercises I put online, and it just hit me the other day. If you would rather just do the paper thing instead of the review exercises for a grade, that's fine. If you want to do both, cool, do both. So what I'll do is if you don't do the chapter 5 practice thing online, I will look at your sample test work and give you a replacement grade.
Does chapter 5 homework close after the test?
Chapter 5 homework will close at 11 o'clock on Thursday a.m. It's best to do it before the test. Are there any requests to open it up through midnight that day? 1, 2, 3? Okay, fine. We will open up through midnight on Thursday. Okay, so the plan is exam on Thursday. There's a sample test posted in Canvas. Take a look at it. I will post my answers tomorrow morning. And then we'll go over whatever questions you guys have tomorrow on the types of question on that or homework questions, whatever you want to do. All right? Have a great day. Do good math and other good deeds.